We've talked before about VORs and how to test VOR receivers, and today we're going to have a look at the instrument landing system. What you're looking at here is an approach plate. It's actually an approach plate for the runway 25 of the Little Rock Air Force Base with the identifier KLRF. And this basically shows pilots how to get to said runway. You see here's the approach path, and at the end here we see a little note. It says Localizer 109.9, and that's megahertz. That's the frequency they dial in their nav receiver in the cockpit. So what you see here to the side is the Localizer path, it's called. And basically, if the airplane dials in this Localizer frequency in their navigation receiver, they're going to get guided down the center line of this Localizer here. And let's have a look at how that's done. So the principle is surprisingly simple. Let's start with the Localizer up here. Basically, at the sometimes it's at the end, sometimes the Localizer is generally in the end, but you can place it anywhere as long as it's somewhere close to the runway, obviously, and it has to be on this axis here, but you could place it closer to here or there. So in this picture it's located at the end of the runway, and that's where it mostly is. And it basically consists out of two transmitters. It's one amplitude modulated transmitter with a 90 Hz modulation tone, and another amplitude modulated transmitter on the exact same frequency, but with a 150 Hz tone. And back in the days, really a long time ago, you could really sit in the cockpit and listen on your headphones, and if you'd hear both tones with same intensity, you knew you were on the center line of this Localizer. And if you'd get more to this side, obviously the 150 Hz tone would be dominant, and moving over to this side, the 90 Hz tone would be dominant. So this is really super simple. Obviously, I mean, this technology has been around for a long time, but it's still being used in aviation nowadays. It's a very important thing. And well, you also get guidance in this plane, and this is called the glide slope. It gives the pilot an altitude guidance how to get down. The principle remains the same. We're having an antenna array here somewhere alongside the runway, and it has two transmitters, one modulated, amplitude modulated at 150 Hz, and the other one at 90 Hz. And the antenna characteristics is so that there's one lobe below and one above, and they're intersecting on the right glide slope here. And again, the same principle applies. If both tones are received predominantly let's start that again. If both tones have the same intensity, you're on the right glide slope. If you hear one of the tones stronger over the other, obviously you're off, and you can tell the direction too. If your 90 Hz tone is dominating, then you're too high. If the 150 Hz tone is dominating, you're too low. It's as simple as this. And since I took this off Wikipedia, here is the Creative Commons attribution. But so it's a very simple principle. Now obviously nowadays pilots don't sit in the cockpit anymore and listen for those tones individually. There are receivers that will automatically indicate where you are in regards to this runway. So let's see how we can test one of those receivers and what's involved. By the way, on a side note, of course you can use two amplitude modulated transmitters with different frequencies, but in reality it's often more practical to use one amplitude modulated transmitter, and the other one is a dual sideband, double sideband transmitter, and for demodulation purposes the receiver just uses the carrier of the other transmitter. So we could use the 150 Hz one here, amplitude modulated, and the 90 Hz one at double sideband. And that way for the receiver in the cockpit it would make no difference, because the carrier of this receiver could be used to recover this signal. So that's a whole lot more power efficient. Okay, anyway, let's have a look at a practical setup, how we can test one of those receivers. Okay, so what you see here is the localizer indication of my Yaesu FTA-550. It is an handheld airband transceiver that can also display localizer information, and it's dialed in at a fictional localizer here on the frequency 110 megahertz. And I can move the needle around here with my test setup. And this test setup is surprisingly simple. Let's zoom out. Alright, so what you see here is the FTA-550 squeezed in between the MDO4000 and the AFG signal generator here. And I'm using the AFG 3102 to generate two signals, our 90 Hz tone and our 150 Hz tone at an equal amplitude of 1 volt peak peak. Actually, I'm a little bit off here. Now we got an equal amplitude of 1 volt peak peak. Alright, next from there it goes into this mini circuit resistive splitter that's used as a combiner to get both signals together. And from there I am going into my beautiful HP signal generator. You can see the settings here. This is from our splitter. This is the combined 90 Hz and 150 Hz signal input going straight in here. The box is tuned at 110 megahertz, -9 dBm. And we are amplitude modulated here through this external reference signal. So if you take another look at our paper here, you see that if the 90 Hz tone is dominating, we should see that we are to the left side of the runway. So let's see what that indication looks like on the FTA-550. So if we just dial the 150 Hz tone down to maybe half of it, we can see that we are to the left of the runway. Now this bar represents the runway basically relative to you, so it means that your runway is off to the right, and that's what we would expect. If you look at this diagram again, we have a more dominant 150 Hz tone, no correction, a more dominant 90 Hz tone now, and that means that we're off to the left and we should move more right to get us back on the center line. So this is really easy when you're flying. You just try to steer your aircraft into this bar. If it moves over here, you try to steer this way, and if it moves over there, which we can of course also simulate, let me get this back to 1 volt peak peak, switch to the other channel. So if I lower the signal here, we should see the needle moving the other direction, and we do. So now unfortunately this FTA-550 does not have a glide slope receiver in it, so I cannot show you the beautiful glide slope at the same time. The higher up module radio, the FTA-750, does have a glide slope in there as well, but that one's horribly expensive. But you get the principle. It's the exact same thing that you would do there. You would just use it on a UHF frequency. Now if you look back at the approach plate right here, down there, Localizer 109.9 megahertz. A pilot does not have to dial in two different frequencies for the Localizer and the UHF glide slope. The frequencies are paired in a way so that the navigational receiver knows where to look for the glide slope, and the glide slope frequencies are in the UHF range. So if you wanted to test a glide slope receiver, all you'd have to do is do the exact same setup in the UHF range. Okay, well, that was the video on the instrument landing system, how to verify your ILS receiver, and I hope you liked it. If you did, give it a big thumbs up, share it with the world, and I'll see you next time.